Welcome to the deep dive. Today, we're jumping into, well, a really fascinating kind of digital world. Think of it like a pocket universe
Hmm.
where artificial life doesn't just get simulated, it actually, learns to survive, thrive, and really master its little digital world, all starting from absolutely nothing.
That's a great way to put it. Yeah. Today we're looking at the digital terrarium. It's this really cool project. It takes Conway's Game of Life, the classic 2D thing.
Right, the grids and pattern.
Exactly. And it blows it up into 3D. And the whole point is exploring how these intelligent AI agents, autonomous ones, can sort of emerge and learn really complex stuff from, well, basically a blank slate.
And this isn't just some thought experiment, is it? This is a real project.
Oh, yeah, very real. It's a C++ project called Game of Life NN. And what's really interesting is the collaboration behind it. It's between a human developer, Lee Strip, and an AI Gemini 2.5 Pro.
Wow. Okay, so human and AI coding together.
Pretty much. They built and refined this specific AI brain. It's a type of recurrent neural network, or RNN, that actually powers these little digital creatures.
And how did that collaboration go? I mean, human working with AI on development.
Well, Shrimp mentioned it was actually his first time doing that, like really closely collaborating with AI, and he said it was positive overall.
Mhm.
Though, not perfect. He did have to step in and correct several errors that Gemini made.
Right. Okay. So oversight is still key.
Definitely. But it really highlights this practical back and forth that's starting to happen between people and AI tools and building things.
Absolutely.
Yep.
So, okay, our mission for this deep dive then. Let's really unpack how these 3D agents work. How they go from, like you said, knowing nothing
Zero.
to having instincts, learning as they go in real time, and then even evolving over generations, becoming, masters of their domain.
Yeah, it's quite a journey.
Should be some real aha moments for you listening.
Ah.
Okay, let's start at the beginning. The genesis. A blank slate comes to life.
Right. So picture this 3D space. It's not just a flat grid like the old Game of Life. It's much richer.
A whole environment.
And this is the terrarium where these agents live.
Exactly. And each agent, each little digital creature has its own brain. And that brain is one of these recurrent neural networks, the LS3D RNN they developed.
Okay, and RNN. So it can process information. Does it have memory?
It does, no
Yeah.
way. That's key for learning and adapting.
Yeah.
The memory in this case is actually pretty simple. It's the agent's current physical state.
Like where it is and which way it's facing.
Precisely. Its position and orientation in the 3D world, it's stored in a technical term here, GLM.mat4 matrix. But yeah, basically its physical status is its memory of the immediate past. It helps it connect actions over time.
So when these agents first pop into existence, created by the simulation, what's in that brain? What does it start with?
Okay, this is the really mind-bending part.
Yeah.
When they're first created, there's a function, simulation.SpawnAgents internal, that does this. The brain knows absolutely nothing.
Nothing at all. No basic programming.
Nope. Zero. Nada.
Inside the code that sets up the brain, the LS3DRN NMLP private constructor, every single connection, every weight in the neural network, it's initialized to a tiny random number, like I think almost zero, but slightly different for each connection.
So it's just noise.
Exactly. It's described as a canvas of random static, completely naive, no built-in instincts, no hard-coded rules about what to do. It has to figure everything out just by interacting with its world.
Wow. Okay. That's a blank slate. So how does it go from random static to something that can actually do anything, let alone survive?
Right.
Let's get into the day-to-day or maybe moment-to-moment life of an agent.
Right. It's this constant loop. Happens incredibly fast, about 30 times a second. You can break it down to maybe 5 key steps. Think of it as a continuous think, learn, act cycle.
30 times a second. Okay, that's
Yep.
rapid-fire living. What's step one for our newborn agent with its brain full of static? How does it even start?
Well, before the learning really kicks in, it has these fundamental hard-coded instincts. Think of them as basic gut feelings. They're not learned, they're just built-in priorities. Primal drives, basically.
Okay, like survival programming, but super simple.
Yeah, exactly. And they're prioritized. Priority number 1, hunger. Always. If an agent's energy drops below a certain threshold, the Hunting's energy threshold, its whole focus snaps to finding food. It enters the hunt state. Look for dinner.
Makes sense. Survival first. What if it's topped up on energy, not hungry?
Then priority 2 kicks in, curiosity. If it's not driven by hunger, it looks around for other agents. If it spots one, it might switch to a roam state and just follow it.
Just follow another agent.
Yeah. And this simple rule, surprisingly, leads to this really fascinating emergent behavior where they start forming herds or groups naturally without any herding code.
Huh. Okay, and if it's not hungry and there's no one around to follow, what then?
Then it hits priority 3, boredom, basically. If conditions 1 and 2 aren't met, it enters an IDL state, just hangs out, waiting for something to change, get hungry, or spot another agent.
So it always has some kind of goal, even if it's just wait.
Exactly. This little state machine always gives it an immediate focus, which is crucial for the next steps.
Right, so it's got a state hunt, roam, or idle. What's next in this super fast loop?
Next up is perception, step 2. Based on whatever state it's in, it gathers sensory data from its environment. It creates what's called a perception vector, like a snapshot of what's relevant right now.
What's in that snapshot? What does it see or sense?
It's very specific to the state. If hunting, it gets the 3D coordinates of the nearest food. If roaming, the 3D coordinates of the agent it's decided to follow.
Okay.
And always, no matter the state, it includes its own current energy level. That's it. That perception vector is the only input its brain receives.
Got it. Goal state, say, relevant sensory input. Brain is still mostly random static at this point, especially early on. So now the learning. How does random static make sense of this? This feels like the core magic.
It really is. Step 3. This is where the teacher forcing happens. It's a really brilliant technique, actually. The simulation itself acts like an all-knowing teacher for the agent.
An all-knowing teacher. Okay, how does that work?
So every single tick, remember, 30 times a second. The simulation calculates the mathematically perfect move for that agent given its current state and perception.
Perfect move. How?
Well, if it's hunting food at certain coordinates, the simulation knows the exact direction and rotation needed to get closer in the most efficient way. It has the right answer.
Okay, so the simulation holds the cheat sheet.
Kind of.
Right.
Then it teaches the agent's brain. It essentially says, okay, brain, when you saw this specific perception, food over there, energy level this, you should have produced this specific output. Move this way, rotate like that. The agent's brain then compares its own output, which remember started random, to the teacher's perfect output. And here's the key. It slightly adjusts all its internal weights and connections, just a tiny nudge.
To be less wrong next time.
Exactly. To be a little less wrong next time, it's a micro-correction.
And this happens constantly, every tick.
Every single tick. So it's not like the agent has to stumble around blindly forever. It gets this continuous, gentle guidance. Nudged towards the right behaviors constantly, it speeds up learning massively.
That makes so much sense. Okay, so it gets the teacher's correction. Does it just do what the teacher said then? Or does it think again?
Good question. That leads to step 4, thinking for itself. Right after getting that nudge, the agent feeds the exact same perception vector back into its own, now slightly tweaked brain.
The same input again. Why?
It's like asking, okay, brain, you just got a little smarter. Based on that same situation, what do you think now? The brain processes the input through its freshly adjusted weights and produces its own best guess for the move.
Ah, I see. Like internalizing the lesson immediately. Learn, then try.
Precisely. It's testing its new understanding instantly.
Okay. So it gets its own best guess output. Then finally,
Step 5, act. The agent takes that output from its brain, applies real-world physics, it can't go faster than max speed, things like that, and then it actually updates its position and orientation in the 3D world.
it makes the move.
It makes the move. And that new position and orientation, that becomes the brain's memory for the very next tick, completing the loop. Ready for the next perception, the next teacher forcing, the next thought, the next action, all in 130th of a second.
Wow. That whole cycle. Perceive, get corrected, think, act. 30 times a second. That paints a picture of really intense, nonstop learning.
It really is.
And you said individual learning is only half the story. What about the bigger picture, generations?
Yeah, exactly. That individual learning is crucial for an agent to, get through its own life.
Yeah.
But the way the whole population gets smarter over time, that's down to good old-fashioned Darwinian evolution.
Okay, survival of the fittest, but for digital agents. How does that work here?
It's pretty direct, almost brutal, you could say. Agents whose brains learn effectively, the ones that get good at finding food, using that loop we just discussed, they gain energy, they survive.
And the ones that don't?
If their brains just don't wire themselves correctly, if they fail to learn efficiently, they can't find enough food, they run out of energy, they starve, and they get removed from the simulation. They become is dead.
Right. End of the line for that agent.
The system's quite neat. When an agent dies, its energy isn't just lost. It gets recycled back into the environment, essentially becoming food for the other agents.
Full digital ecosystem. Very efficient. So success means survival. How are those successful traits passed on? How does reproduction work?
Right. So when an agent gathers enough energy, it hits a threshold. Energy will produce, it makes a copy of itself. It reproduces.
And the child agent.
The child is an almost perfect copy of the parent. And crucially, it inherits the parent's brain, not a blank slate one. It gets all the learned weights, all the connections the parent painstakingly developed through its lifetime of teacher forcing.
So it starts with all the parent's knowledge. That's Lamarckian almost, inheriting acquired traits.
In a way, yes. It gets that huge head start. But you noticed I said almost perfect copy.
Ah, okay. There's the catch. What's the difference?
Mutation. This is the evolutionary twist. When the child inherits the brain, a tiny random change is introduced. There's a mutate function called specifically childbrain.mutate, 0.0001F.
What does that do?
It randomly tweaks a very small percentage of the brain's weights, just nudging their values slightly. It's a random perturbation.
And that small change could be good or bad.
Exactly. That tiny mutation might make the child slightly better, maybe a bit faster at processing food location, or more efficient in its movement, a beneficial mutation. Or it could be detrimental, make it slightly worse. Or have no real effect, it's random chance.
So natural selection acts on these tiny variations introduced at birth.
Precisely. Over hundreds, thousands of generations, agents lucky enough to get those beneficial mutations. They're more likely to survive, find food, reach that reproduction threshold.
And pass on their slightly superior mutated brain.
You got it. While agents with detrimental mutations tend to die out, so the population as a whole, generation by generation, gets better and better adapted. Better at the one poor goal. Find food, survive, replicate.
So what does it look like visually, going from that random cloud to this?
Well, the transformation is amazing to watch. You start with this chaotic mess of agents just bumping around randomly because their brains are static.
Right, the initial state.
But over time, as learning kicks in and evolution selects for the learners, you see this beautiful emergent order appear. Agents actively hunting down food patches. You see that herding behavior we talked about becomes this intricate dance of digital life, all sprung from randomness, simple rules, and learning.
That is genuinely incredible. We've gone from this canvas of random static to intelligent, adaptive agents. It really shows the power of combining those simple instincts
The gut feeling.
with that constant real-time teacher forcing.
Microcorrections.
And then layering Darwinian evolution, the mutation and selection on top.
It's a potent mix. They build on each other to create complexity from almost nothing.
And we shouldn't forget the very start, the human-AI collaboration that even built this simulation. Lee Strip working with Gemini, the human guiding, correcting. It's like collaboration happening at multiple levels here.
That's a great point. The process of creating the terrarium mirrored, in a way, the learning process within it. Iterative refinement, correcting errors, building complexity.
It really makes you wonder, doesn't it? If you can get this kind of a complex, adaptive, seemingly intelligent behavior emerging from such simple rules, random starting points, and these learning loops in a digital box, what does that suggest about, the fundamental principles behind intelligence, maybe even life itself, in our own universe?
Yeah.
Could it also be built on surprisingly simple foundations?
It's definitely provocative. And it makes you think, what happens next? What other surprising things might emerge if you let these digital organisms evolve for even longer, or maybe change the rules of their world slightly?
Yeah, what new emergent properties are waiting to be discovered in future versions? A lot to think about there.
Absolutely. Leaves you pondering.
Indeed. Well, that's all the time we have for this deep dive. Until next time, keep exploring, keep asking questions, and keep diving deep.